Good morning to all of you. Last class we discussed about Shannon Fano coding, in which we have been solved some problems. Let me continue what we discussed in the previous class. I have been given the problem. A DMS emits 7 messages. M1, M2, M3, M4, M5, M6 and M7 with probabilities 0.4, 0.2, 0.12, 0.08, 0.08, 0.08 and 0.04. Apply Shannon-Fano coding procedure. Find efficiency and redundancy. As we discussed in the last class, it would have been seen that given messages can be partitioned into 2 groups, keeping 0.4 in one group, keeping remaining in other group. If you add remaining messages, it will be 0.6. So I can have 0.4 in first group, remaining in other group. That is the way it can be solved. Otherwise, I can take 0.4 and 0.2 in one group. If you add it together, it will be 0.6. Remaining will be 0.4. So there are 2 ways that you can do the first partition. As we discussed in the last class, case 1 I have been taken as keeping these 2 in one group, that is x1 will be x1, x2 and x2 will be the remaining messages in other group have been taken as x3, x4, x5, x6 and x7. Would have been applied Shannon-Fano coding, would have been calculated efficiency as eta is equal to, of course, would have been calculated L bar, average code word length. It will be 2.52 bits per message. Efficiency eta will be 96.032. We computed redundancy also in the last class. Redundancy R will be, this is in terms of percentage, 3.97%. Now let us repeat the procedure for case 2 and let us conclude which way of doing partition will lead for better efficiency. Case 2, as I said earlier, I'll be taking 0.4 in one group and remaining will be in other group. So my x1 will be only one message, say x1, and x2 will have remaining. x2, x3, x4, x5, x6 and x7. Now let me apply Shannon-Fano coding procedure for the case 2 and let me find out what is the L bar value, what is the eta and what is R. Based on that, let me make the comment which way will lead for better efficiency. So as we know, according to the Shannon-Fano coding theorem, first you have to write the messages in descending order of probability, then you have to partition given message set into 2 most equiprobable subset for which you have to assign a 0 and 1. The same procedure will be repeated until you have been left out with only one message in each subset. So let me write messages in descending order of probability. So write down messages, then write down the probability. Already the messages are in descending order, so I can write it as it is. That is M1, M2, X1, X2, X1, X2, X3, X4, X5, X6 and X7. The probabilities are 0.4, 0.2, 0.12, 0.08, 0.08, 0.08 and 0.04. Let me find code word or encoded message. Then let me find code length. Code length is LK, the probability is PK. Now, as I said earlier, I'm going to keep 0.4 in one group, remaining are other group. So I have to divide, I have to partition here. I have to assign 0 to messages contained in one subset and 1 to messages contained in other subset. So assign 0, for remaining all I have to assign 1. So 1, 1, 1, 1, 1, 1. You have to proceed as long as you have only one message in each subset. Now you look at it here, there is only one message, I cannot do partition. So remaining, you look at it here, we have 6 messages. Now I have to split it most equiprobable subset. That means if I add these two, I'll get 0.32. If I add remaining 162428, so I can split it here. Some cases you can split exactly equal, some cases you cannot split exactly equal. That is the case you have to look at where you can do most equiprobable subset. So I have to split it here. Assign 0 to messages in one subset and assign 1 to messages in other subset. Now if you look at it here, we have 2 messages. Again I can do partition. Since only 2, I can split it here only. So I have to assign 0 to one group, 1 to other group. Now if you look at it here, we have 4 messages. I have to split it most equiprobable subset. So if I add these two, I'll get 0.16. If I add these two, I'll get 0.12. So I have to split it here. I have to assign 0 to messages in one subset and I have to assign 1 to messages in other subset. Again you have to look at it here, we have 2 messages, split it equally, assign at 0 and 1. Here again we have 2 messages, split it here, assign 0 and 1. Now I have been applied Shannon-Fano coding procedure. Now I am in the position to find the code length. Code length is nothing but number of bits in the encoded message. If you look at it here, there is only 1 bit, so code length is 1. There are 3 bits, so code length will be 3. Here again 3 bits, code length will be 3. Here again we have 4 bits, code length will be 4. Again 4 bits, code length will be 4. 4 bits, code length will be 4. 4 bits, code length will be 4. As we discussed in the earlier classes, more the probability of occurrence will have less number of bits, less the probability of occurrence will have more number of bits. That's the way we improve the efficiency of the communication system. After doing coding, you have to find the efficiency, where efficiency is given by the formula. Efficiency eta is equal to h of x, entropy of the source by average code word length L bar. The formula for finding entropy h of x is equal to summation k is equal to 1 to n pk into log pk to the base 2. As I said early in the previous discussion, when you have to the base 2, you cannot use it in calculator. That is the case you have to. If x to the base 2, that can be written as log x to the base 10 divided by log 2 to the base 10. That means you have to divide with log 2. So already we computed entropy for this problem. The entropy h of x is equal to 2.42 bits per message. It's same because it depends upon only probability of occurrence. It does not depend upon the code word. That's what the entropy will be same like what we computed. So 2.42 bits per message. Now let us calculate L bar, average code word length. The formula for computing L bar, average code word length. L bar is equal to summation k is equal to 1 to n pk into lk. So there are 7 messages we have. So k varies from 1 to 7. pk into lk. We know the probability of occurrence. We know the code length lk. So That is 0.4 into 1 plus 0.2 into 3 plus 0.12 into 3, 0.08 into 4. No, since it is 3 times, so we can write 3 into 0.08 into 4 plus 0.04 into 4. If you calculate the value for L bar will be 2.48 bits per message. Now, if you calculate efficiency, eta is equal to h of x by L bar. H of x is 2.42 divided by 2.48. It will lead for 0.976. Therefore, efficiency in terms of percentage will be 97.6%. Once you know the efficiency, you could able to compute redundancy R. Redundancy R is equal to 1 minus efficiency. So 1 minus 0.976. So it will lead for the R value as 0.024. If I express redundancy in terms of percentage, R will be 2.4%. If you compare the average code word length for case 2 as well as case 1 we had L bar is equal to 2.52 bits per message. Now it has been reduced to 2.48. As the L bar is reduces, efficiency will increase. So from this I can conclude that doing partition in the second case leads for better efficiency than the first case. So whenever you apply Shannon coding theorem, you have to see what are the possibilities that the code word, what are the possibilities that message can be partitioned, and you have to look at it which system will lead for better efficiency. This completes our discussion about Shannon coding procedure. Now, take down one problem as assignment and submit it via Google Classroom. Please note down the problem. Assignment 1. Consider the messages M1, M2, M3, M4, M5, M6, M7 and M8. M1, M2, M3, M4, M5, M6, M7 and M8 with the probabilities 1 by 2, 1 by 4, 1 by 16, 1 by 16, 1 by 32, 1 by 32, 1 by 32 and 1 by 32. Apply Shannon coding procedure. Apply Shannon coding procedure. Find efficiency eta and redundancy R. Of course, at this point of time, you might be knowing how to solve this problem. First, you have to write the messages in descending order of probability. Then you have to look for partitioning the messages into two most equiprobable subsets. Assign 0 and 1. Proceed until you have been left with only one message in each subset. Then apply the formula for finding efficiency and redundancy. As we discussed earlier, there are two methods of doing source coding. One is called Shannon coding. The other one is called Huffman coding. Now let us discuss about what is Huffman coding, how the efficiency can be computed using Huffman coding. First, let us see the procedure for Huffman coding technique. As we discussed in Shannon coding, here also the messages to be written in the decreasing order of probability. So first, you write the messages in decreasing order of probability. For the source symbol of lowest two probability, you assign a 0 and 1. Then you combine the two lowest probable symbols. So you get a new symbol whose probability will be equal to sum of two original probabilities of earlier symbol. Then you get a new symbol. Again, you place it in the list in the descending order. You have to proceed further until you have been left with only final list of two source symbols for which a 0 and 1 to be assigned. So again, I will repeat the procedure. First, you write the messages in descending order of probability. For the two lowest probable symbols, you assign a 0 and 1. Combine two lowest probable symbol, you get a new symbol whose probability will be equal to sum of two original probabilities. Then again, place that new symbol in the list in the descending order. You have to proceed until you have been left out with only two source symbols for which a 0 and 1 to be assigned. To find the code word, you have to track backward and you have to look for zeros and 1 assigned to that symbol as well as its successors. But tracking backward would be so difficult, so you track it forward but write it in reverse order. So the code word can be obtained by tracking backward and looking for zeros and 1 assigned to that symbol as well as its successors. Instead, I will be doing forward tracking, I will be writing it in reverse order. Now let us solve one problem so that you can easily understand how the Huffman coding can be improving efficiency of the communication system. Let us take one problem. Consider 5 messages. Consider 5 messages. M1, M2, M3, M4 and M5 with the probabilities 0.4, 0.2, 0.1, 0.2 and 0.1 respectively. Use Huffman coding technique. Use Huffman coding technique. Find efficiency and redundancy. Now, let us apply the Huffman coding procedure. First, you write the messages in descending order of probability. Now, you look at it. We have 0.4, 0.2, 0.1, 0.2, 0.1. It is not in the descending order, so you arrange it in a descending order. So, write down the message and probability in descending order. So, among all the 0.4 is highest, so M1 is going to have highest. So, M1 with 0.4, then you look at it, next is M2, 0.2, here also you have one more 0.2, so M2 will be 0.2 and M4 will be 0.2, followed by 0.1, 0.1, M3 and M5 as 0.1, so M3 is 0.1 and M5 is also 0.1. So first messages are written in descending order of probability. Now what I have to do is, for the lowest probable symbols, two probable symbols, I have to assign a 0 and 1. So here M3 and M5 are having 0.1, 0.1. Probabilities are low, for which I am going to assign a 0 and 1. Now I have to combine these two symbols. So if I combine 0.1 plus 0.1, it will lead for 0.2. Again, that 0.2 I have to place it in the list in the descending order. When you place it, there are two issues. One issue you will get getting it. If I combine these two, you will get 0.2. I can arrange that 0.2 above this 0.2 or below this 0.2. If you move this combined symbol above this 0.2, we call it as a moving as high as possible. If I place it down this, we call it as a moving as low as possible. Always it is advised to go for as high as possible. We'll discuss one problem based on that, by moving combined symbol as low as possible. From that, we can conclude the variance is going to be very low when you move the combined symbol as high as possible procedure. So if I combine these two, I'll get 0.2. I have 0.2 here. I have to keep above this point. That means I have to keep this 0.4 as it is. Because of combining these two symbols, I get 0.2. That I have to bring it up in the list. Now this point I have to bring down. This point I have to bring it down. One thing you have to keep it in your mind, whenever we are going to combine, the list of source symbols will be reduced by 1, because earlier we had 5. Since I am going to combine these two, I will get 4. I have to proceed further until I have been left out with only 2 messages for which I have to assign a 0 and 1. Now if you look at it here, I have 0.2, these are the 2 lowest probable symbols. I have to combine these two, I have to assign a 0 and 1. If I combine this, I will get new source symbol 0.4. Already I have 0.4, so this 0.4 should be kept above that 0.4. That is called as high as possible procedure. So bring this 0.4 up. This is due to the combination of these two symbols. Bring this 0.4 down. Bring this 0.2 down. One thing you have to remember at this point of time, whenever you are placing the symbols, it has to be in the descending order of probability only. Now, for the lowest 2 probable symbol, I have to assign a 0 and 1. Now, if I add this 2, I will get 0.6. I have 0.4 here, supposed to be at the top. So 0.6. This 0.6 is obtained by combining these two source symbols. Then bring this 0.4 down. Now assign. Now you have been left out with only 2 source symbols. Final list of 2 source symbols for which I have to assign 0 and 1. I'll repeat the procedure. First, you write the messages in descending order of probability. For the 2 lowest probable symbol, assign a 0 and 1. Combine these 2 lowest probable symbols. You get a new symbol. Again, you place it in the list in the descending order. You have to proceed until you have been left out with only 2 source symbols for which a 0 and 1 to be assigned. Now, you have to find the code word. As I said earlier, code word can be obtained by tracking backward and looking for zeros and 1 assigned to that symbol as well as its successor. But doing backward is difficult. That's what we do forward, and we write it in reverse order. Now I write on the code word. So again write it message, probability, code word and code length. Probability, code word and code length. Probability is PK, length is LK. Now write down the messages. M1, there are 5 messages, of course we have been seen. M1, M2, M3, M4 and M5. Now let us find the code word for every messages. Before that, write down the probability. For M1 the probability is 0.4. For M2 the probability is 0.2. M3 the probability is 0.1. For M4 the probability is 0.2. And M5 the probability is 0.1. Now let us find the code word for M1. Code word for M1 can be obtained by track this arrow mark. Track it, track it, track it. 0 is assigned here. Track it, 0 is assigned. As I said earlier, we are going to track forward, so write it in reverse order. So if you track this, you get 0, 0. Even you write it reverse order, you will get 0, 0 only. So code word for M1 is 0, 0. Similarly, track it for M2. Find the code word. So for M2, track it, track this. We have been assigned 0. Track this arrow mark. We have been assigned 1. So if I write it in reverse order, it will be 1, 0. For M3, track this arrow mark. We have been assigned 0. We have been assigned 1. We have been assigned 0. 0, 1, 0. Even if I write it reverse order, it will be 0, 1, 0. Similarly, do it for M4. Track this arrow mark. We have been assigned 1. Track this arrow mark. We have been assigned 1. So 1, 1, if I write it in reverse order, it will be 1, 1 only. For M5, track this. We have been assigned 1. We have been assigned 1, 0. So if I write it reverse order, 0, 1, 1. So the code word can be found by tracking this arrow mark but writing it in reverse order for every message. Now you know the code word, you know the probability of occurrence. You are in the position to find code length. Since there are 2 bits, code length is nothing but number of bits in the code word. Since we have only 2 bits here, the code length will be 2. The code length for this is 2. The code length for this will be 3. Code length for this will be 2. Code length for this will be 3. So code length is nothing but the number of bits in the encoded message. Now let us find the efficiency. We know the formula for finding efficiency. Efficiency is equal to efficiency eta is equal to h of x, entropy of the source divided by L bar, where L bar is nothing but average code word length. Now let us find entropy. Entropy h of x is equal to summation k is equal to 1 to n pk log pk to the base 2. As I said earlier, it is there into the base 2. So convert to the base 10 by dividing with log 2. By dividing with log 2. Therefore, this equation can be rewritten as, so the value for log 2 is 0.3010. So 1 by 0.3010 into summation k is equal to 1 to n pk into log pk. Now to the base 10, where k varies from 1 to n. Since there are 5 messages, this can be rewritten as minus 1 by 0.3010 summation k is equal to 1 to 5 pk log pk to the base 10. 0.4, substitute P1, P2, P3, P4 and P5. So you will get 0.4, that is minus 1 by 0.3010 into 0.4 log 0.4 to the base 10 plus 0.2 log 0.2. There are 2 point, but anyway, there are 2.2s. So I can write 2 into 0.2 log 0.2 to the base 10 plus, there are 2.1s. So 2 into 0.1 log 0.1 to the base 10. If you simplify, you will get the value as 2.2 bits per message. Sorry, 2.1293 bits per message. Similarly, you find out L bar, average code word length. L bar is equal to summation Lk into Pk, or Pk into Lk, where k varies from 1 to n. Here 1 to 5. K is equal to 1 to 5 Pk into Lk. We know the probability of occurrence and we know the length of the code word also. So 0.4 into 2 plus 0.2 into 2 plus 0.1 into 3 plus 0.2 into 2 plus 0.1 into 3. If you compute the average code word length L bar, it will be 2.2 bits per message. 2.2 bits per message. Now we know h of x, we know L bar, so we are in the position to find efficiency eta. Therefore, efficiency eta using Huffman coding is efficiency eta h of x. H of x is 2.1293 divided by L bar. L bar is 2.2. If you find the value, it will be 0.9642. 0.9642. If I express efficiency in terms of percentage, eta will be 96.42%. Now let me calculate redundancy for the given source. Redundancy represents amount of duplicate information. Redundancy R is equal to 1 minus efficiency. So 1 minus 0.9642. Therefore, R in percentage, redundancy in percentage will be, sorry, 1 minus this, R will be 0.0036. To express R in terms of percentage, R will be 3.6 percentage. So by means of doing Huffman coding technique, you could able to improve the efficiency of the communication system. One thing you have to remember at this point of time, we know the efficiency is given by h of x by L bar. As the L bar value leads to be very low in the case of Huffman coding, it will lead for better efficiency. That's what the Huffman coding technique is also called as minimum redundancy code or maximum efficiency code. Thank you. When we come for next class, we'll discuss some more problems based on Huffman coding techniques. As I said earlier, by moving combined symbol as low as possible and as high as possible, there will be only in terms of variance is going to be only changed, but efficiency and remaining entropy is going to be same. That we'll discuss in the next class.
So good morning. In the last class, we left with the mapping of section C2. So let us continue from that. So we completed mapping of section C1 and as well as C2. So just let I recall. So mapping of section C1 we have got with respect to the polar plot. So this is the diagram. So in the f of S-plane contour. So the crossover point here it is minus 0.00417 K. Similarly, we also completed mapping of section C2. So in the mapping of section C2, this varies from, that is R have 0 magnitude and phase angle is varying from, that is 0 e power minus j3 pi by 2 to radius with 0 and e power plus j3 pi by 2. So we are aware of that. This is in the UJV domain, that is f of s domain, 0 degree, minus 90, minus 190, minus 270. So here it is started from minus 270, then minus 180, minus 90, 0, 90, 180 and then 270. So this is the arrow direction, but this consists R tends to be 0. So this is what we have seen in the last class. So let us now move to the mapping of section C3. So mapping of section C3. So actually for the mapping of section C3, we need to submit or substitute S is equal to j omega, where here omega can be varied from minus infinite to 0. Because in the S plane, now this is your section C3. So here it is 0 minus, whereas here it is from infinite. So that for the omega we need to substitute minus infinite to 0. But however, before finding for mapping of section C3, this is just opposite of your section C1. Say this is your C1, whereas C1 varying from 0 to infinite. So that is, since C3 is just the inverse of the C1, what happened in the f of s plane? The f of s plane contour will also be a inverse for the mapping of section C3. So here just we are going to reverse this. So since C3 is opposite to C1, the mapping of section C3 in the f of s plane will also be a just inverse diagram. So here from, that is started from here and then end up here. So just a reverse of this, so we can able to draw. So what about the directions here? The direction is just opposite. Okay. So here it is inward. So here it is an outward direction, but the crossover